So today we're going to talk about normalization in this lecture, and we're going to look at further forms of normalization in the second part of the lecture. We'll have a break in between, as we normally do. So we're going to try to look at how you might design a database using this bottom-up approach. You know that the last week we talked about designing databases, and we looked at the top-down approach, which was building the ER diagrams. So last week we looked at how you would design a database using ER diagrams. This week we're going to look at how you might design a database looking at normalization, which is a bottom-up approach. And so we're going to look at things like, I don't know why at the end it has done that, the text. But for some reason it's kind of like gone funny. Anyway, what you have to read is chapter 14, I believe, of the Connolly and Beck book. There are two chapters. The first one is for the first part of the lecture. The second one will be for the second part of the lecture. And the rest of the reading is optional. So, what we got to understand first is what is normalization. And we have talked about it in previous lectures. We have mentioned it at least because we said that this was something that Code developed. If you remember, Code was one that talked about the relational model, and he also came up with further work on relational databases, which is all of these concepts of normalizations, which give us a set of properties. They give us relations that have better properties. So they're important in the sense that if you normalize your relations, then they're going to be a better design than if you have unnormalized databases. So what we're looking at is a series of tests that we do for a particular normal form to ensure that, for example, it is in first normal form, or second normal form, or third normal form, or Boyce Codd normal form. So each normal form has a set of tests that we have to carry out to ensure that the relations that we're dealing with are in that particular normal form. If the relations fail the test of normalization, then we decompose them. We break them down into smaller relations. And how do we decompose them? If you think back over the previous lectures, you remember in relational algebra, we talk about selection and projection. Projection allowed us to take a set of attributes and put them in a different relation. So that is how we are going to decompose a larger relation. In effect, we will be using the projection in relational algebra to break the bigger relation into smaller relations that meet the required normal form, whether it's first, second, third, and so on. The most commonly used are first, second, third, and Boyce Codd normal form. And then there are others that we will look at in the second part of the lecture, which can occur sometimes. There can still be anomalies, even when we are in third normal form and Boyce Codd normal form. So the other normalizations, fourth and fifth, try to prevent the problems that can still happen with data when you are in this high normal form. And the idea of normalization is that we need to understand the concept of a functional dependency in the data. So we will look at the concept of functional dependencies, try to understand what that is, and once we have done that, we will be able to understand how we normalize a particular relation. So we said that normalization is good because it means that the relations that we create have a set of desirable properties that make them better. The desirable properties that normalized relations have are that they have a minimal number of attributes, which are the minimum number necessary to support the enterprise. We know that we have to create this database which supports the business of the enterprise. So if we do this using normalized relations, what we're going to have is a minimal set of attributes that we need in order to meet the requirements of the enterprise. So it's going to be good from that point because we have, if the number of attributes is minimum, we are keeping less data, we don't have to store it, look after it, etc. So that is always going to be good. The other thing that happens with normalization is that attributes that have a close relationship with one another, which is in effect a functional dependency, are going to be put together in a relation. And in normalization, in effect, what we're doing is, if you think about writing a piece of text, and they have ever told you how you write well, in a paragraph you don't mix two different concepts. Normalization is a bit like that. In a relation, we don't want to mix two different kind of like objects. So the idea of normalization is that we are going to keep things that are logically related in one relation, but if things are not logically related, then we will send them to different relations. So that's another good property. And the final very good property is that we're going to have minimal redundancy. Remember that we said already that redundancy was problematic for the database environment because it leads to inconsistencies in the data, etc. We're going to look at some of those problems that are going to appear where we have redundancy, and we're going to see how normalization deals with the redundant data. And it allows control redundancy. So the redundancy that is going to be left after normalization would be things like foreign keys and primary keys which are repeated, but because of something, they're repeated because we have to link tables together. So the redundancy that will be left after normalization will be controlled redundancy. So those are the properties that we want to realize when we normalize relations. So what is it for? As I said to you, you could use it as a form of a design technique. And in that, it will be a bottom-up technique. Because what we do in normalization is we identify attributes, etc., and then we build relations from them. So it's a bottom-up approach. Instead of the ER diagram, when we look at the kind of overall concepts and then we break down the diagram as we go along, with normalization, we do it the other way around. However, designing by normalization is quite a hard thing if you have a very large database. So normally, we wouldn't use normalization to design in this way. What we do use it for is to check the results of normalization that is done in a top-down fashion. So what we do is we design our database, as we learned last week, with an ER diagram. Once we have done that, we can check that every relation that we have produced is normalized. And if it is normalized, our design is good. If the relations that we produce are not normalized, then we should improve on our design and make sure that we normalize the relations that we have. So in that way, we're not going to use it as a design tool. We are going to use it as a tool to check on a design that we made by a top-down approach. Are we all happy with that so far? Good. So that is why we're going to learn about it. So what are the kind of problems that we might get if we have redundancy in the data? Because we have said one of the things that normalization is going to help us to do is to deal with redundancy problems in the data. So of course, if we have redundant data, for a start, we are wasting storage space because we are storing duplicate data, which we don't need to store. So that is going to be wasteful for a start. And if you have a very large database and the redundancy is large, it could become quite costly to store all the additional data, look after the data, etc. And also, the other problem that we're going to have when we have redundant data is that we are going to have what we call update anomalies. And that means that as we update, insert, delete, modify data, if there is redundancy, we are going to end up with problems that occur because of the redundancy. So let's say that we have, for example, a table like this, a relation like this, which is the teaching allocation relation. And I have the staff ID, the name, the module code, and the description. So this is a relation, it's not a normalized relation. And I know that because there are redundancy in the data. For example, if I look here at the module called CMPSMB21 and the description, that is stored twice. So there is redundancy in that data. Okay? And equally, if I look at the stuff I did, again, this is stored twice. Okay? So I have redundancy in the data. So what kind of problems am I going to have? Apart from the fact that I am storing the data more times than I need to, so I am using more space, what is happening there? So one of the things that is going to happen is I'm going to have insert anomalies. So when I am inserting another record, which references the CMPSMB21 record, that is already there. So I have to make sure that the data that I insert is consistent with the data that is already there. If then suddenly I put a different description, then I have introduced inconsistencies in the database. And that, from a database point of view, is a very bad thing to do. So we want to keep our data consistent. Equally, if I want to enter the details of a module, I have to enter the details of a member of a staff. If I don't know the staff allocated to that module, I'm going to have to enter nulls. But nulls might be part of the primary key, so I won't be able to enter that. So I have problems when inserting data because I have to make sure that the data I insert is consistent, but also because to insert a given stuff I have to insert the module. To insert a given module I have to insert the details of the stuff. So that is going to be problematic when I insert. What about when I try to delete? If I delete, for example, the last record that references CMP SMB21, then the information about the module and the stuff associated with it, if the stuff is not associated with another module, will go as well. So I might delete information on a member of a staff because the last time that he's associated with a module goes. So I'm assuming that this is the staff information that I keep. Okay? So I'm seeing there that this is not a good idea because when I delete data, again I'm going to have anomalies. I might lose more data than I want to. And what about if I want to modify the details of CMP SMB 21? Let's say that the description changes slightly. I don't just have to change it once. I'm going to have to go through every tuple where that description is associated with the module name, and there is more than one, and I'm going to have to make those updates. So I don't update once, I have to update a number of times. So that is what I would call an update anomaly. So we have insertion anomalies, deletion anomalies, and modification anomalies. And to avoid all of that, what I have to do is decompose that relation into smaller relations. If you think about what I told you before about mixing things, in that relation I'm mixing two separate things, the stuff and the modules. They are kind of separate objects, but they are represented in the same relation, and this is causing me trouble. So what I want to do, and what normalization is going to allow me to do, is to split the data and send the data that is related to the same object to one table or relation, and the data that is related to the other object to another table. So I'm going to break down the original data, the original relation, using the projection that we learned in relational algebra. I'll take some attributes, I send them to one table, I'll take some other attributes, and I send them to another table. And when I do this, the two things that I have to make sure that I can guarantee as I break my larger table into smaller tables, to make sure that normalization is correct, I have to guarantee these two properties. The first one is called the lossless join property, and it tells you that any instance in the original relation can be identified from the entries in the smaller relations. So for example, if I'm looking for a particular member of a staff, if I could find it in the larger relation, I should be able to also find him in the smaller relation. If I'm looking for information on a module, if I could find it in the original relation, I should be able to find it in the smaller relations. So that is what we call the lossless join property. We don't lose any data as we divide the larger relation into smaller relations. The other thing that I have to guarantee is what they call dependency preservation property. And that means that the constraints that I had, if any, on the original relation, I must be able to maintain in the smaller relations. So that is looking at the constraints of the data. So if there was a particular constraint that said a member of a staff should not be associated with more than 3 modules, that constraint should be something that I can maintain in the smaller relations. So those are the two properties that I have to guarantee as I decompose my larger relation into smaller relations. Are we all happy with that?
Is it just possible to ask, is it possible that you could possibly show us this, like a really...
I will. As we go along, we are going to look at examples of this.
Okay.
So at the moment I'm just talking about it, but the examples will come. Because I know at the moment it's abstract, but it will come as a form of an example. So we are going to look at it now. But before we look at it, we need to understand one fundamental concept, and that is the concept of a functional dependency. Because that is how I said we are going to look at normalization. What I want to do is identify the data that should be together. So that I do by identifying what I call functional relations in the data. Functional dependencies in the data. And these are associations between attributes in the relation. For example, if I have an attribute A and an attribute B, which are both attributes of a relation, R, then I can say that B is functionally dependent on A if each value of A in the relation is associated with exactly one value of B. So for example, if I give you in my supplier part shipment tables, if I say to you part number in the part table, each part number is associated with one color. Okay? So there is a functional dependency between the part number and the color. If I give you the part number, I know the color. So there is a functional dependency. The opposite is not necessarily true. Functional dependencies have a direction. So the part number is associated with a specific color. A color may be associated with more than one part number. Okay? So the functional dependency goes in the direction of the arrow. Equally, if I say to you in a student database, a student number, I know that that leads to only one student name. So there is a functional dependency between a student number and a student name. For a given student number, I can only get one student name. The opposite might not be true. I could have the same student name associated with a number of student numbers. For example, if I have John Smith, I might have more than one student name associated with one number. But for a given student number, I can only get one name. So that is a functional dependency. Do you all understand that? So the color of the part is functionally depending on the part number, and the relationship in that case is 1-to-1. For a part number, I have one color. But the opposite is not necessarily true. For a color, I might have more than one part number, because the functional relationship goes on the way in which it is specified. So let's see now an example of this. Let's see that I have my parts table, and I've buried it slightly to fit my purpose here, because what I have here is, let's say that I look at some documentation. This is perhaps before I have a database. And what I have is information on the spreadsheets that is kept by the company. And in one of these I have the supplier number, the name, the status, and then the city, and then for each supplier I have a series of shipments that have been associated with that supplier. So I know that supplier 1 shipped part 1 in a quantity of 300, part 2 in a quantity of 200, and so on. Okay, so I have all my shipment information there. And on the other hand, I have the part table with the part number, the name, the color, the weight, and the city. Now, what I learned slightly differently here is that I'm saying the status is associated with the city. So, for example, Paris is always going to have a status of 10, London is going to have a status of 20. So, I'm saying that in this example this works like this, because I can then explain to you how normalization works. So, in this particular example, I'm saying the status is associated with the city. So, if I have London, I have one status. If I have Birmingham, I have another status. So, this is what we call an unnormalized relation. It's not in any normal form. Could this fit the relational model? Could I store this information in a relational model? No, because why couldn't I put that into a relation? What is the problem that I have? I have S1, Smith, 20, London, and then I have P1, 300, P2. Why couldn't I put that in the relational model? Somebody must know that. Because at the intersection of a column and a row, I can have only one value. Does that happen there? No, because I have repeating values for part number and for quantity. So this does not fit into the relational model. It's not a relation, because at the intersection of a row and a column, I have a number of values. So that is not complying with the relational model. It's what I call an unnormalized relation. Okay? So it's not really suitable for staring as a relation. So the first thing I have to do is make it comply with the relational model. And that will mean putting it in first normal form. So when we put it in first normal form, we actually introduce redundancy initially, but then we get rid of it. But initially, the first thing that we have to do for it to be in first normal form is make it comply to the relational model. And that means that at the intersection of a column and a row, I must have a single value. And that means that I have to deal with these repeating groups, and I do that by what I call flattening the table, which is taking each of S1 Smith 20 London and repeating it for all of the individual shipments. Okay, so that's what I call flattening the table. So I end up with S1 Smith 20 London P1 200 or 300, S1 Smith 20 London P2 200. So I have dealt with the issue of the repeating groups by flattening the table. That is now in first normal form. I have duplication in it because clearly S1 Smith 20 London appears a number of times. So it's not a particularly good table at the moment, but it meets the standards of the relational model. I could store it as a relation. Are we all happy with that? Yes? Good. So that is all you have to do if you had a question on normalization. They go like this. The first thing that I ask normally is identify problems with the table which lead to anomalies like insertion anomalies and so on. Okay? So if you were to do that in that table, you will say to me, okay, there is a number of repeating kind of like tuples for S1 Smith 20 London. So if I try to insert a new shipment, I have to make sure that the S1 Smith 20 London is consistent with the previous tuples. If I deleted the last shipment for S1 Smith, I will lose the information on S1 Smith. If I had to insert a new shipment, I'll have to make sure it's consistent with the information there. If I have to modify it, I'll have to modify it a number of times. So these are kind of the anomalies that you can detect in the table. Do we all know how to do that? Yes? Happy? Okay, so having done that, then you will say, now I'm going to make this table into first normal form, if it was not normalized at all. So I flatten the table, and I produce something like this. There is redundancy, there's still problems, but we have a table in first normal form. And from there, let's look at what second normal form might mean. Now, what you have to know as well is that each normal form relies on the previous normal form. So if I say to you, how do you define second normal form? It must be in first normal form, and there is additional condition. If I say to you, how do you define third normal form? It has to be in second normal form, and there is an additional condition. Every normal form relies on the previous normal form. Okay? So in second normal form, what we have is that the relation must be in first normal form, i.e. there are no repeating groups, and every non-primary key attribute, remember that one of these tables must have a primary key, so we have a primary key, and we have the attributes that are not part of the primary key. All of the attributes that are not part of the primary key should be fully functionally dependent on the primary key. So that is what we're looking for to decide whether a table is in second normal form or not. So to do that, we need to identify the functional dependencies and make sure that every attribute that is a non-key attribute is fully functionally dependent on the key. If there is a partial dependency, then what we're going to do is we're going to break down the bigger table by decomposition, which we do by projection in relational algebra, and we will send the determinant is the first part of the functional dependency, so we will send the determinant as the primary key with all of the attributes that are dependent on it to a separate table. Okay, so I will decompose the original relation, and I will send, for all the partial dependencies, they will become a different table with the determinant being the key and all the attributes that are dependent on it being part of that smaller table. So that's how we are going to do this. And we're going to remove using projection. So let's look at the functional dependencies that there were in the table that I had. So if I look at my previous table, I can know if I have the supplier number, then I know the supplier name. So there is a functional dependency between supplier number and supplier name. Obviously, to understand functional dependencies, you need to have a certain understanding of the data you are going to store. So you need to understand your domain and what you're doing. But we know that here, if we have a supplier number, I know what the name is. So there is a functional dependency there. I also know that if I know the supplier number, I know the status of the supplier. Okay, that's also a functional dependency. I know that if I know a supplier number, I know the city of the supplier. Okay? I said in this example that the status is determined by the city. So I have an additional functional dependency that I says, if I know the city, I know the status. Because London is associated with 10, Paris is associated with 20 or whatever. So there's a functional dependency there in my data. And when I look at my parts table, I have the part name is functionally dependent on the part number. The color is functionally dependent on the part number. The weight is functionally dependent on the part number. And the city for the part table is functionally dependent on the part number. Additionally to that, the quantity that I have shipped is not dependent on the part number and it's not dependent on supplier number. It's dependent on both. So to know the quantity, I must know the supplier number and the part number. Those two things determine the value of quantity. Okay? So those are my functional dependencies. Are you happy with that? Yes? You understand? So if you have identified those, and we look at the previous table now, in my previous table, my primary key must be a combination of supplier number and part number, because that's what is unique, okay? So my primary key in that table is defined as being supplier number and part number. So this is in first normal form. To be in second normal form, every non-primary key attribute must be fully functionally dependent on the key. Is this true? Is every non-primary key attribute fully functionally dependent on the key? Considering that the key is supplier number and part number. No, because we have any of those dependencies are not. The only full functional dependency on the key is quantity. Okay, quantity is fully functionally dependent on the key. All of those attributes are partially dependent on the key. They are dependent only in the S number. Okay, so they are partial dependencies. Here, if this is the parts table, I'm okay, because these attributes are, supposing that I had a part table. No, I still haven't got a part table. I'm looking at only one table. So again, these are, jumping in. So there, no. That relates to the, I am right. This relates to the part table, which I haven't giving you an example of what you know from previous things. So all of these things are okay, because if I had a part table and P number was the key, these things are fully functionally dependent on the key. But I think I gave you the example of the table in the first slide, didn't I, earlier on. So if I look at the example that I gave you earlier, just not to confuse you. Yeah, so we had these two tables, okay? So I've looked at the functional dependencies of both. For this one, if P number is my key, my primary key, I'm okay because all of the other attributes are fully functionally dependent on the key, given the functional dependencies I identified. But this one, I'm not okay because I have partial dependencies. So this table is in second normal form, but this table is not in second normal form. So I have to do something about it. So what do? I have to decompose the table into smaller relations. And every partial dependency, I need to send to a different table with the determinant as the key. So that means that I have to look at S number, status, and city and put them in a separate table with S number as the determinant. And I do that by decomposition using projection. And also, here I am okay because this table was already in second normal form, so I don't have to do anything about it. Okay? So what I have to do now is I have to decompose by using projection. So I will say send this set of attributes to a different table. So I will say S number, S name, status, and city form a different table with S number, which was the determinant, being the key. On the other hand, quantity and S number and part number are decomposed to a different table with S number and part number being the key because they were the determinant in the functional dependency. So I now have two tables which are in second normal form. because every non-primary key attribute is now fully functionally dependent on the key of the table. Are we all happy with that? We understand second normal form so far? Okay, so if we do understand second normal form, then we can move on to third normal form. Now, as I said, every normal form depends on the previous one. So for something to be in third normal form, it must be in second normal form. That is the first thing, always. So if I'm looking at is something in third normal form, the first question I have to ask is it already in second normal form? And then there's an additional question. No non-primary key attribute is transitively dependent on the primary key. Now, when we look at the transitive dependency, what we're talking about, if you remember about transitivity from maths, I have that if B is dependent on A and C is dependent on B, then C is transitively dependent on A. And that is what I don't want to have. I don't want to have transitive dependencies if I am in third normal form. Okay? So, if I have transitive dependencies in my data, I need to again decompose the relation and send them to a separate table with the determinant as the key. I'm always doing this decomposition. So, did I have some transitive dependencies there? Did I? Yes, I do, because I have the city is dependent on the supplier number. The status is dependent on the city. Therefore, the status is transitively dependent on the supplier number in that particular example. So that is what I will call a transitive dependency. And that means we're not in third normal form. And there is still going to be problems with redundancy. Because, for example, if we have here, we have Paris twice and 10 twice. So there is still redundancy in this table. If Paris is always associated with one particular status, then I don't need to store it twice. Okay? I have redundancy in that table. I have to deal with it. So I will deal with it by separating that and sending it to a different relation. So what I am going to end up with is that I take my transitive dependency and I send it to a separate table with the determinant as the key. So I need to break down my original relation, which was in second normal form, and say, okay, in third normal form, I have the S number, the S name, and the city, and then I send the transitive dependency to another table, which is going to have city as the key and a status as the additional field. Now I have dealt with the redundancy, because I'm only going to store 20 ones for London and Paris 10 ones. So I don't have that form of redundancy there. Are we all happy with that? Okay. So then my finalized design to third normal form is going to have the shipment table, which will have the S, the P number, and the quantity, which I got from the second normal form. The P table, which stayed as it is because it's already in third normal form. There are no transitive dependencies there that we could identify. So that's already in second normal form. And because there's no transitive dependencies, it's also in third normal form. And then I have the third normal form tables that I've derived, one of which has the S number, S name, and city, and then the city and the status. And I have dealt with the problem of redundancy in the data. And therefore, I should have none of these update anomalies that we talked about before.
So, for the third, second relationship, status is transitive dependent.
The status is only now dependent on city. So this is a separate table. Yeah. Okay. I have one non-primary key attribute. Now, status is dependent on the primary key of this table. So this table, because I have to analyze each relation independently of the others. This relation, the only dependency is the status is dependent on city. So a non-primary key attribute is dependent fully on the primary key. So it's in second normal form. And there are no transitive dependencies because there are no other attributes.
Yeah, but city is dependent on supplier number.
City, yeah, but they are separated now. So city is dependent on supplier number, but this is the key. So here you don't have transitive dependencies in this table anymore. Yeah? This table is in third normal form because there are no transitive dependencies here, and there are no transitive dependencies here. And if you look at the amount of duplication that I had, I've dealt with it, because before the problem I had is I was storing London 20 twice. Now some same suppliers may have the same city, that is fine, but I'm only storing the status 1 for each of them, so I dealt with the redundancy. Yeah?
Yeah.
So you have to look at each table independently of the previous or the other tables. Are they in a particular normal form or not? So you analyze the dependencies within a table, and then if there are no partial dependencies and no transitive dependencies, then that table is in third normal form. Okay?
So if there is some repetition in the third form, it's okay? I see there's queries.
Yeah, because you cannot avoid the fact that some individual, so for example, you can have suppliers with the same city, but, and that is just the nature of the world, you have different suppliers with the same city, that is fine, because you have to associate a particular city with the supplier, but knowing the supplier number, you know the city, right? But before, if you hadn't separated those two, you would have stored London 20. Each time you store London, you will also store the status. But the status is the same for any given city, so you only need to store it once. So by doing the third normal form, you deal with that redundancy. Okay? So yes, you have more than one supplier might be in London, but now because the status is dependent on the city, you only store that once in third normal form. So you've dealt with the redundancy. It doesn't mean that the redundancy doesn't mean that you're not going to have the same value appearing in the database more than once. It means that where you have redundancy, it is controlled redundancy. So for example, I might have many students studying the same module, that is fine. But I don't want to put the module description for each student that is studying it. I only want to have the module description once. And then, yes, I might have many students associated with one module, that is fine. It's a different type of concept. Are you all happy with that? No? Good. So, if I show you that, what are the problems with that particular relation? So I have there a relation enrollment, where I have the registration number and the name, the unit code and the description. So what happens if I try to add a student that is called 013456 for King A? What's the problem with that? So I have that table with the registration number of the student, the name, the unit code that they enroll on, and the description. And now I want to add a student. What happens? What's the difficulty?
Okay, insert anomalies, null and the unit code.
Yes, because you might not know yet what he's enrolled for, and I'm going to have to end up having nulls in the enrollment if I don't know what he's enrolled for. What about if I want to rename CMPS MB21 to Information Management? If I want to change the description of that particular unit, CMPS MB21, what's the problem with that?
Again, update anomalies, so you only change one of the...
Yes, I could have a number of tuples, and I have to go through each of them making the same change. And if I don't, I will have inconsistent data, because one tuple will refer to information management, the other one will refer to databases. So it will be inconsistent data. What if I want to delete Jones J? What happens with Jones J? I get rid of Jones J. Let's say he's the last student that takes graphics.
You're going to get rid of graphics.
Yes, I lose the information on graphics as well, because he was maybe the last student. Then I don't have information on graphics. So that is not a good idea. Those are the type of anomalies that I have. And here is a little problem for you. So here I have a table displaying temporary staff contracts. And the time spent by staff working at hotels, the staff number is unique for each member of the staff. So what I have there is if I have a pen, yes I have staff number, contract number, hours, staff name, hotel number, and hotel location. So what I have there is staff that are assigned to different contracts, okay? And what are, if I look at that table, what are the functional dependencies in that table? So give me any functional dependencies that appear there.
Hotel number to hotel location.
Hotel number to hotel location, so there's a number name, number. So if I know the hotel number, I know the hotel location. What else? Staff number determines staff name. So if I have the staff number, I know the staff name. What else?
Contract number?
Yeah. If I know contract number, what do I know?
Hotel number, I guess.
I know hotel number. So a given contract number is associated with one hotel number.
Also, staff number.
I think actually, if you look at it, a given hotel number, contract number alone, is not associated only with one hotel number. So in the same contract, there might be more than one hotel. So that association, that functional dependency does not hold, because I have a contract number here and the same hotel number there. So I must need something else to establish the. So it might be something like a staff number and contract number establishes. So here we have a scenario where we have a contract that is a member of the staff, but maybe they go to more than one hotel. Okay? And what else do I have? What other functional dependencies do I have there?
What about staff number and contract number and hours?
Yep, the staff number and contract number gives me the hours that are worked in the contract. What about contract number alone? What does it give me? Not much, I think. So that's fine. So how do we now break that down then? Is that in first normal form? Yes, because at the intersection of a tuple and a row, there is only one value. Is it in second normal form? What will be the key of that particular table? The primary key. A staff number and something else, because a staff number alone is not unique. So it's going to be a staff number and contract number together, because if you think you have the same staff appearing more than once. Okay? So staff number alone is not the primary key, but a staff number and contract number might be the primary key. So if that is the primary key, these things are fully functionally dependent on the key, but the staff number is not fully functionally dependent. Incidentally, we know hotel number and we also know the location of the hotel, yeah? If we know staff number and contract number, we also know the location of the hotel, right? And we know the hotel number. So, in terms of partial dependencies, I can see that if this is my key at the moment, ours is fully functionally dependent on the key, and hotel number and hotel location, but staff name is not fully functionally dependent on the key. So to take it to second normal form, I have to decompose the original relation and send that to a different relation with a determinant as the key. So I need to end up with a relation that has a staff, which has a staff number and a staff name, for which a staff number is the key. Now that is got one attribute which is fully functionally dependent on the key, so I am okay. And then I need to have another one which has a staff number and contract number and hours and hotel number and hotel location. And that, let's say, I call that contract. And my key is going to be that, because that's the determinant of the dependencies. So now, this is okay because every non-primary key attribute is fully functionally dependent on the key. So it is in second normal form. This is in second normal form, and this is in second normal form. Is it in third normal form? I have a transitive dependency here because I have the hotel location is dependent in the hotel number, and they are dependent on the key. So I have a transitive dependency there. So to make it in third normal form, I have to deal with the transitive dependency. Okay, so I have to then break this down, and I'll end up with a contract which has, so this is second normal form, but for third normal form, this one stays, because this is in second and in third normal form. There is no transitive dependencies in this table. But this one, I have to break down by decomposition. So I have to end up with a staff number, contract number as before, which are the key, hours, and hotel number. But to that, I have to add another one, which is having hotel number and hotel location. And that is the key, because that is the transitive dependency that I have at the top. So that is a transitive dependency. And the other one, this is a partial dependency. So now I have my tables, that, and that, and that is my set of third normal form